So let's talk about the property of aldehydes and ketones. You could see here that with the pi bond of the carbonyl group, that the electrons can be pushed to the oxygen. That creates partial positive charges on the carbon here and on negative charge on the oxygen. So remember, these are resonance structures. We don't really draw the carbonyl group like this, but it just demonstrates to you the charge distribution is unequal. This is a very polar bond. And we've got a partial positive character on this oxygen here, or sorry, on this carbon here. Partial positive right there. And that's pretty much, that explains how this reacts. So we've got a carbonyl group here. I've even made a little model of it for you. So here's carbon double bonded to oxygen. And notice it's trigonal planar, so it's flat. So if you were to lay this down, then a nucleophile tends to come and attack from the top or from the bottom. So you could see in this diagram here. And what happens when the nucleophile attacks is we have rehybridization, so we turn into an sp3 carbon. So this electrophilic site is where the nucleophile attacks, and so the nucleophile is electron rich, the electrophilic site is electron poor. So that would be the carbon. So whenever you see a carbonyl from now on, I want you to draw that it's partial positive right here at this carbon. That will help you remember what happens next. So after the nucleophile attacks, the electrons go up to the oxygen, and now this is where we have a center for electrons, and so that becomes a more basic site, the oxygen, and that is what will act as the base in the next step. Usually what happens here is then we want this to become neutral, so usually grabs a hydrogen from water or slightly acidic solution. Now, based on electronic factors, that means based on charge distribution, which carbonyl would be more electrophilic, an aldehyde or a ketone? So let's stop there. So electrophilic means more positively charged. So let's say we have a ketone, and let's say we have an aldehyde. Now, if we're looking at how electrophilic they are, we're talking about how positive this carbon is. So let's say this is partial positive and this is partial positive because they're both carbonyls. But this question asking which would be more electrophilic, this ketone or this aldehyde. Let's think back to carbocations. Remember when you had a carbocation, you had R groups, and a tertiary carbocation has more R groups, and that would be more stable. So the more R groups there are, the more induction there is, right? The charge density can go toward the positive, therefore stabilizing it. So based on that, who do you think would be more stable? Well, hopefully you think that the more R groups there are, the more the charge can be distributed toward that positive center. That means it's more stable. So this would be more unstable then, meaning it's got more positive charge that hasn't quite been neutralized somewhat by its neighboring R groups. It has less R groups. In terms of steric factors then, steric factors means you've got a nucleophile, maybe it's bulky. I'm just trying to come in and do that a nucleophilic attack of that carbonyl carbon. Okay, who's going to be affected more by sterics? So in this case, you could picture a nucleophile coming in, and if there's more R groups and they're bulky, then that can really slow down the nucleophilic attack. So in that case, here we have less steric hindrance for an aldehyde, and we have a more positively charged carbon because it's less stabilized due to less R groups. So for both reasons then, an aldehyde is more reactive than a ketone. And that's an important point that we'll come back to several times during our topic here of aldehydes and ketones. And also will come up later when you're analyzing unknowns. And it turns out that aldehydes are also more susceptible to oxidation as well. So aldehydes oxidize more easily than ketones. That makes sense because aldehydes can turn into carboxylic acids. So you'll see that when you're trying to analyze an aldehyde, you might actually get results that point to a carboxylic acid, but it's because the aldehyde had oxidized. So there are differences definitely between ketones and aldehydes and how they react, even though they look very similar to each other. And for the most part, they do react very similarly. So I want you to remember this basic mechanism, which is that the nucleophile comes in, attacks this carbonyl carbon, the electrons flow to the oxygen. So you make a bond, you break a bond, and you get this intermediate that is sp3. We call this a tetrahedral intermediate because that's what it is. So from here, I'd like to apply this many times with different possible nucleophiles for you to see. So just FYI, we're going to see many reactions in the next bit, but remember that they're all the same reaction. They're all this reaction. So let's start with reaction number 1. This is a Grignard reaction. I think many of you remember this reagent because it's pretty easy to use. I mean, not in real life. I think you saw in lab it was actually quite difficult to get a Grignard reaction going because it's sensitive to moisture. But for the most part, you know, organolithium means the lithium is positive. That makes this methyl quite negative, good base, strong base, good nucleophile. Same thing here with the Grignard reagent. It's the methyl group, the R group, that is reactive as a nucleophile. So you could take either one of these and attack it at the carbonyl carbon. Because remember, our electrophile is right here. Our nucleophile is right here or here. Okay, you could take either of those. All right, so from here, and I'm sort of drawing the arrow here because I'm picturing the, you know, if I completely ionize this bond, which it's not really, I would have a negative charge here and I'd have a positive charge on the lithium. But another way that people usually draw this is they draw the R group with the bond to the lithium and then they show that bond breaking with an arrow here. So that's technically that's better. All right, let's draw our tetrahedral intermediate. After this tetrahedral intermediate, you can imagine we want to neutralize this. So that's what this water and dilute acid workup is for. So in the end, we get an alcohol. We started with 2-butanone. So we started with 2-butanone, or butan-2-one, and we ended with 2-methyl-2-butanol, or butan-2-ol, if you prefer. All right, so there's that reaction. All right, so pretty simple to follow, and you actually already covered it last quarter anyway, but for those of you who don't remember, try to review that. We have basically the same thing with reaction number 2 here. Instead of R group, we have a hydride. So these hydrogens here are the reactive parts, the nucleophilic parts. And so I just simplify that into H-. That usually works pretty well for most mechanisms. Some mechanisms you actually have to write it out and figure it out. But for the most part, if you see borohydride or aluminum hydride, go ahead and draw the hydrogen attacking here. It's the whole thing, the BH4 and the ALH4 group, but this is good enough just for, you know, figuring out what your answer is going to be. So our tetrahedral intermediate now looks like this. Difference is the H instead of an R group. And then after acid workup, you just neutralize that with a lone pair on the oxygen. And so we get different products here. So instead of an R group like we had here, we just have a hydrogen. So we just did a reduction, just a carbonyl turning into an alcohol. Whereas in the other example above, we have a carbonyl turning into an alcohol, but with the addition of an R group right here. All right, so alkylation is what we call this one. Whereas this one, we just simply call it reduction. For each reaction we're going to learn, there's going to be a lot of reactions this quarter, sorry to say, but we'll let you do a lot more too, though. So for all the reactions you learn, please write out a basic summary. You know, this with this turns into this. And then on a separate sheet of paper, go ahead and draw out the mechanism, or on the same sheet of paper if you want. Just draw out the mechanism and how it works. And then when you have all of them written down, you'll start to see patterns. You'll see, oh yeah, this is basically doing the same thing as here, but these parts are different, like this. These parts are different here, the reagents. But it will allow you a chance to really see the patterns, the commonalities that will help you remember these things. Okay, and let's skip this one for right now. We'll come back to it. I'd like to cover this one right here because it's very similar to what we just did. So for the addition of cyanide, You could call it reaction number 3 if you want. And this addition of cyanide is basically just like the ones we did before. So I'd like you to take a moment and show me how you use this nucleophile to attack here. And then after water workup, you get a new functional group that we haven't seen before called a cyanohydrin. Okay, go ahead and show me this mechanism. All right, so we're back, and I'm going to use the cyanide. Now, cyanide is not always provided to you like this, okay? Just FYI, often you see HCN or you see NaCN, and you're supposed to know, oh, I used the cyanide, okay? So especially NaCN is what this mechanism is for. HCN, we would have to react the acid part first, which I'll show you in a bit. So let's say you have NaCN, and so you need to know that for Na sodium cyanide, you use the cyanide, and hopefully you know how to draw that out. Okay, so we take the lone pair on the carbon, do our nucleophilic addition. This is called acyl nucleophilic addition, or nucleophilic acyl addition, because acyl is referring to the carbonyl group. Here's our tetrahedral intermediate, and then we use our acid to protonate there. All right. If you were to have HCN as your reagent, then what we would do is protonate first here, and then because this is our basic site, remember from our previous question about which site is basic, we said the oxygen. So oxygen tends to, because of its lone pairs, it can get protonated. It's usually a pretty good base when it comes to being an acidic solution. So then we end up with this protonated ketone first, and then the cyanide can come in and attack here, and then we can eventually get our cyanohydrin that way. So just be aware of those two separate mechanisms.